All right, so today we're learning two additional tests. So you have Keeper 3.4, the integral test, and the P-series test. And so let's start with the integral test. And basically what the integral test says is if your function is continuous, positive, and decreasing, then we could take the integral of the function to figure out if the integral converges or diverges. If the integral converges, then our sum of our series or our sum of our sequence converges, and if the integral diverges, then our series diverges. So here's an important note that we need to remember for our integral test. Remember, we need to check first to see if it's positive, continuous, and decreasing. However, just remember that it doesn't actually have to be decreasing everywhere. It just needs to decrease over time. So it might increase a little bit at the beginning, or increase, decrease a little bit at the beginning. But as long as over time, off to infinity, it decreases, that's okay. It still checks out and it still works for the integral test. All right, so example 1, we want to determine if it converges or diverges. So what I'm going to do is I'm going to check my conditions for the integral test. The first condition, I know that it is positive, and I'm doing that by inspection. I'm not doing really any math there. I just know since n starts at 1, my numerator is positive and my denominator will also always be positive, so the series is positive. I'm also checking to see if it's continuous, and so I'm looking for any holes or jumps of the function. I notice that there is a vertical asymptote at -3/5, but that vertical asymptote is outside of my domain since n starts at 1. So that -3/5 doesn't bother me, which tells me that this function is continuous. And so the next thing I want to check is decreasing. This is actually the only one that you actually need to show for AP purposes. The other two you're basically doing by inspection, but decreasing you must show. And so decreasing, you can either do show that the term that you're on is greater than the next term, or you can take the derivative and show that the derivative equals a negative number. So I'm going to show it using the first way. And so the current term is n, and the next term is n plus 1. I know that n is less than n plus 1. Now what I'm going to do is I'm going to build my series. So I'm trying to build 2 over 3n plus, or 3 plus 5n. So the first thing I'm going to do is multiply by 5, and I know 5n is less than 5n plus 1. And then I know that 3 plus 5n is also less than 3 plus 5n plus 1. Now when I flip it to make it a fraction, I have to remember to flip my inequality sign. So I have 1 over 3, 3 plus 5n is greater than 1 over 3 plus 5n plus 1. And then if I multiply everything by 2, I know that 2 over 3 plus 5n is greater than 2 over 3 plus 5n plus 1. All right, so example 2, I'm trying to determine again whether the series converges or diverges. Basically what I do is I look at the series itself to see if it can be integrated. And I'm looking at this and I notice that it's probably something that I can integrate. So I'm going to go ahead and try to use the integral test. Now again, to use the integral test, you have to check your conditions. The first condition, I know that it's positive because n starts at 2. So my numerator, I'm going to get a positive number, and my denominator, I'm going to get a positive number. I also know it's continuous from 2 to infinity because the only issue I have is at -1. At -1, I would have a vertical asymptote. But again, because our domain starts at 2 and it goes to infinity, -1 is not an issue. So this is a continuous series. And then decreasing, again, I must show. Now, again, I can show that the term I'm on is greater than the next. Or, like I was saying in the previous example, I can go ahead and just take the derivative. And so for this, I think it will be a little bit easier just to take the derivative and show that the derivative is negative. And so when I take the derivative of the function, I need to show low d high minus high d low over low low is negative. So here we have low d high minus high d low over low low. When I clean that up, I get negative n to the 4th plus 2n over n cubed plus 1 squared. When I'm looking at this, if I were to plug in my first n of 2, my numerator is definitely going to be negative. So 2 and above is going to be negative. And then my denominator, because it's squared, is always going to be positive. So I have a negative number over a positive number, which is a negative number, which tells me that this function is decreasing. All right, so now that all my conditions are met, we can go ahead and integrate. So we have the integral from 2 to infinity of x squared over x cubed plus 1 dx. Remember, because it's going to infinity, we have to use improper integration. So we have to change that infinity to a t and run the limit from t to infinity. So we have the limit from t to infinity of 2 to t of our function. And then I'm going to use u substitution to integrate that. And so when I use u substitution, I get 1/3 ln x cubed plus 1 from 2 to t. And so next I'm going to plug in the 2 and the t, plugging in the t first, of course. So I have 1/3 ln of t cubed plus 1 minus 1/3 ln of 9. When I plug in the infinity, I'm going to end up with infinity, which tells me that since the integral is divergent, the series is also divergent by the integral test. All right, so the next test we want to look at is our p-series. And so we've already learned some of this with our improper integrals. Well, basically what you want to do is if you have a series of the form of some number over into some exponent, if that exponent is greater than 1, it's going to converge. If it's less than or equal to 1, it's going to diverge. All right, so it says determine whether this series converges or diverges. And so the first thing I'm going to notice is that it is of the form of a p-series because it's 1 over into some power. And that power in this case is pi. Pi is greater than 1, therefore the series converges by the p-series test. All right, so next, same situation. It is of the form of p-series, a number over into some power. The power in this case is 2/5, so p equals 2/5, which is less than or equal to 1, which tells me, since it's less than or equal to 1, that this series diverges by the p-series test. All right, so next we have 1 over the cubed root of n cubed. And so basically our p this time is 1, because cubed root of n cubed is the exponent will become 1. So p equals 1, which is less than or equal to 1. Therefore, our series diverges by the p-series test, which sometimes you'll also see it called harmonic. So whenever you have 1 over into the first power, again, a lot of times some people, or depending on what text you're reading, will call it harmonic. So you can say it diverges because it's harmonic. All right, next we have determine whether the series converges or diverges. The sum from n equals 1 to infinity of n to the pi over n to the e. First thing I'm going to do is rewrite this to make it look more like a p-series. And so I have 1 over n to the e minus pi. And so my p in this case is e minus pi. We know that e is like 2.7 and pi is 3.14 or whatever. And so I know when I subtract that, it's going to be less than or equal to 1, which tells me that the series diverges by the p-series test. All right, example 7, we have the sum from 1 to infinity of 1 over n times the square root of n cubed. And so again, I'm going to rewrite this to look more like a p-series. And so I'm left with 1 over n to the 5/2. My p in this case is 5/2, which is greater than 1, which tells me that the series converges by the p-series test.